LC times I of Z is equal to 0. So these are called the telegrapher's equations for the infinitely long transmission line. Okay, so that's what we learned from last previous class. And we also learned that the general solution for the telegrapher's equation is V of Z is equal to, we have a right traveling wave, V plus e to the negative j beta z, plus a left traveling wave, V minus e to the j beta z. Okay, and also for the current I of z, we have a right traveling wave, current wave, I plus e to the negative j beta z, and a left traveling wave, I minus e to the j beta z. Okay, and so this is the z-axis, okay, along the transmission line. And we know that this transmission line has its own characteristic impedance, which is, let's say this is Z0. Okay, so we can determine the relation between the voltage and the current by this characteristic impedance, which means this current I of Z can be written as V plus over Z0 times e to the negative j beta z minus, for the left traveling wave we have a minus sign here, and this is V minus Z0 e to the j beta z. Okay, so this is the general solution for the telegrapher's equation for this homogeneous infinitely long transmission line we learned about. Okay, so here you can see that the coefficient for the right traveling wave V plus and the coefficient for the left traveling wave V minus, they are two independent variables. Okay, they are independent. They can be chosen as with arbitrary values. Okay, and what happens is when we terminate this transmission line, let's say we have a transmission line looks like this. We have an impedance, a load ZL here. Okay, so if the transmission line is terminated like this, then it turns out these two variables, V plus and V minus, they are not independent anymore, because we actually introduced a new boundary condition for this circuit. Okay, so let's say this coordinate system, this is the z-axis, okay, and this point where the load is z equals 0. Okay, and on the left we have z equals negative L, where L is the distance between a point to the load. Okay, but because we set this z-axis like this, is a negative number. I mean the z-axis is a negative number. Okay, so now we have a new condition from the VI relation from the load, that since here is z equals 0, right? So V0 over I0, it must be equal to ZL, right? Okay, it must be equal to ZL. So we need to take into account this new condition we have here. So actually the physical picture here is, usually we treat a transmission line, we think we have some kind of a source here, okay, and this source will launch a right traveling wave, and this right traveling wave V plus with magnitude V plus, this right traveling wave will hit this load ZL, and because this VI relation must be satisfied, So a reflected left traveling wave will be reflected by the load. So we have a reflected left traveling wave. Okay, so that's the physical interpretation about this problem. So as I have said, because of this new condition we have, we have the general solution for V here, right? So that means V0 over I0 is equal to V plus V minus divided by V plus over Z naught minus V minus over Z naught must be equal to ZL, right? This, we just plug Z equals 0 into these two expressions. Okay, so the magnitude of the right traveling wave and the left traveling wave must satisfy this equation, which means V plus and V minus, they are not independent anymore. If you specify a value of V plus, then you can determine the value of V minus. Okay, so now we just have one independent variable, and from this physical interpretation, we know that this independent variable should be V plus. Okay, we launch a source, the source launch a red traveling wave with V plus to be the magnitude, and the red traveling wave gets reflected by the impedance. Okay, so that's the physics here. So we can write V minus as, because it depends on V plus here. Okay, because it depends on V plus here, so we can write a reflection coefficient gamma L times V plus. So this actually agrees with our physical interpretation that the left traveling wave is reflected because of the reflected right traveling wave. Okay, so with this in mind, we know that V naught here, V0 here over I0 here is equal to V plus gamma L V plus, right? And I0 here is just V plus over Z naught minus gamma L V plus over Z naught, right? And this is equal to ZL. Okay, so now we can solve for the reflection coefficient because we know this equation, and so this is essentially V plus times 1 plus gamma L divided by V plus times 1 minus gamma L is equal to ZL. Let me see. Is equal to ZL over Z naught. Okay, and then you can cancel this V plus. So you can express gamma L in terms of ZL and Z naught. Okay, so gamma L is equal to let me see, gamma L is equal to 1 plus, gamma L is equal to ZL minus Z naught divided by ZL plus Z naught. Okay, and also ZL over Z naught can be expressed by 1 plus gamma L divided by 1 minus gamma L. Okay, so we call this ZL over Z naught to be the normalized impedance, the normalized load impedance, ZNL, because we just take the characteristic impedance Z naught as a reference impedance. This is a normalized impedance. Okay, so accordingly, we can express gamma L in terms of this ZNL here, the normalized impedance. which is ZNL minus 1 divided by ZNL plus 1. Okay? And accordingly, on this terminated transmission line, again, we have z equals 0 here, and this is a positive z-axis, and this is, for example, z equals negative L. Okay? So on this transmission line, we know that V of z, the voltage, which is a function of the z coordinate, is equal to V plus times e to the negative j beta z plus V minus e to the j beta z. And now we know the relation between V plus and V minus, right? So this is V plus times e to the negative j beta z plus gamma L e to the j beta z, right? So now we have the linear superposition of the right traveling wave and the reflected left traveling wave. Okay? So similarly, we can write down the expression for the current I of z to be V plus over z naught times e to the negative j beta z minus gamma L e to the j beta z. Right? Okay? So any questions so far?
When you first defined it, was it also supposed to be minus?
Which one?
The I.
This
the
one?
On the first page, you defined it as plus, I believe.
Oh yeah. Yes, it is a plus I minus, but if we express the IZ in terms of V, we have a minus sign in terms of V and the characteristic impedance. Remember from last lecture, the right traveling wave gives us V plus over I plus is equal to Z naught, right? But for the left traveling wave, V minus over I minus is equal to negative Z naught.
Okay.
Okay? So that's where this minus sign comes from. Okay?
Thank you.
Okay, sure. Any other questions? Yeah.
You just teach the last equation.
Here?
Yes.
Okay. Okay. So, good. So we have the expression for the voltage along this transmission line as well as the current along this transmission line. Okay? So now if I specify the z-axis, z coordinate, let's say z equals z naught, then we can define a impedance, an input impedance at this point, actually at arbitrary point. Okay? We just have, let's say, z in at z equals 0, z equals z naught is equal to v z equals z naught divided by I z equals z naught, right? So this is just the input impedance if I look to the right to this transmission line. Okay? And we can just plug these two expressions into this impedance. Okay, so we'll get the generalized impedance. Actually, we can get z as a function of z, right? It's equal to v plus e to the negative j beta z plus gamma L e to the j beta z divided by the current, which is v plus over z naught e to the negative j beta z minus gamma L e to the j beta z. Okay, and we can cancel this v plus here. What we have is, let me see, z naught e to the negative j beta z plus gamma L e to the j beta z over e to the negative j beta z minus gamma L e to the j beta z. Okay, so this is the input impedance at arbitrary point along the z-axis. Okay, and also we can define the generalized reflection coefficient. For example, if I look from here, the v minus at z over v plus at z is equal to a constant here, right? Which is the reflection coefficient at this point. I call it gamma z. Okay, because gamma L is the reflection coefficient at z equals 0, only due to the impedance, the load impedance. And as we move to the left-hand side, the ratio between v minus to v plus is not a constant, it's a function of z. And we call that function the generalized reflection coefficient. Okay, does that make sense? Okay, so since we have the expression for both v of z, v plus of z, and v minus of z, so this is actually equal to v minus of z over v plus of z, which is v plus times gamma L times e to the j beta z over v plus e to the negative j beta z. Okay, because essentially the right traveling wave and left traveling wave, they have different dependence on this exponential term. Okay, one is minus j beta z, one is just j beta z. Okay, so this is gamma L. Let me see. Gamma L times e to the 2j beta z. Okay, so as we can see, as we move this observation point from the load to the left, this reflection coefficient gamma of z will change, but this is a periodic function. Okay, because of this exponential term with imaginary argument. Okay, so you can imagine that this gamma of z is periodic. It's a periodic function. I think the periodic is 2 beta z equals like 2 pi. Z must be pi over beta, or beta z is equal to pi. This is its periodicity. Okay. So now we have for a terminated transmission line, we have the input impedance at arbitrary point, we have the reflection coefficient at arbitrary point. Okay, so what we can do actually, we can also express the ZZ over here, the input impedance at arbitrary point. We can express this Z in terms of the reflection coefficient at arbitrary point. So Z of Z is equal to, let me see, is equal to Z naught 1 plus gamma Z divided by 1 minus gamma Z. Okay, which is Z naught 1 plus gamma L e to the 2j beta Z 1 minus gamma L e to the negative e to the 2j beta Z. Okay, so we have the other expression of Z here, and we have ZZ here. We have gamma of Z here, and it's very easy for you to verify that these two expressions are the same. Okay, so which means once we have the reflection coefficient gamma z or gamma L, we can get the input impedance at arbitrary point z of z. Okay, and also we can express the reflection coefficient at arbitrary point in terms of the input impedance at that point. Okay, so gamma z is equal to Zn of z minus 1 divided by Zn of z plus 1, where Zn of z is the normalized input impedance, okay, which is z of z over z naught. Okay, so we get one, either the input impedance or the reflection coefficient, we get the other. Okay, so they're related to each other. Okay, and so if we use the fact that, let's say we have z of z here, right, and if we set the z-axis as like the where the load is z equals 0, and this is a positive z, and on the left we have z equals negative L, right? If we just plug z equals negative L, so z of negative L is equal to z naught zL plus j z naught tangent beta L over z naught plus j zL tangent beta L. Here we just used that e to the 2j beta z is equal to cosine 2 beta z plus j sine 2 beta z. We can get this, well, alternative expression for z of z. Okay, because usually we set the positive z-axis to be pointing to the right-hand side, so we have z equals negative L on the transmission line, and this is the expression in that case. Okay, and so we have derived these general expressions for a terminated transmission line. Okay, now we will discuss two special cases. The first one is a shorted termination. Okay, shorted termination. Okay, so the transmission line is terminated by a short circuit like this. Okay, this is ZL equals 0. Okay, so again, for this case, what condition, what VI condition this short circuit gives us? Suppose this is VL, this is IL. What condition do we have? Yes. Yes. So the actual condition we have is actually VL is 0, right? Which means if we still set the z-axis to be like this, and this is, at this point is z equals 0, we have V of 0 is equal to 0, right? Which means V plus, or V of 0 is equal to V plus V minus is equal to V plus times 1 plus gamma L is equal to 0. Okay? Which means gamma L must be negative 1 in the short terminated case. Okay? So in this case, Z, the input impedance, Z of negative L, Z z of negative L is equal to J Z naught tangent beta L. Okay, so we can see if we write this as J x, because tangent beta L is a periodic function, then this x, if we plot the graph of x, it will look like this is beta L, this is x, will look like this. So I believe this is a pi, this is 3 pi over 2, it will look like a tangent function. Something like this, right? Which means if I change the beta L, the beta L is also called the electrical length of this transmission line, because essentially we are comparing its actual length L to the wavelength, which is contained in beta. Okay? So if we change this electrical length beta L, the reactance Jx, the reactance X will change from a positive value to a negative value to a positive value to a negative value, which means this transmission line will behave like an inductor. This is inductive reactance, right? And this is capacitive reactance. So this transmission line will behave like inductor and then capacitor, inductor, capacitor. Okay? Depends on the electrical length beta L. And specifically, if we have a very short transmission line, that means a very short, shorted termination transmission line, okay? Which means beta L is much smaller than 1, then tangent of beta L is approximately equal to beta L, right? Okay, so in this case, Jx is equal to J Z naught tangent beta L is approximately equal to J Z naught times beta L. Okay, and since Z naught is equal to the square root of L over C, right? Where L and C are the inductance and the capacitance of the transmission line per unit length. Okay? And beta is equal to omega times the square root of LC. Okay? Then times L. And this is equal to J omega times big L small l, which means we are actually have a linearized inductor. Okay, because L is the inductance per unit length. And this L is the actual length of the transmission line. Okay, and we can call this to be J omega, the effective inductance. Okay, which means when the electrical length is very, very small, a shorted transmission line just behaves like an inductor. Okay? Does that make sense to everybody? Okay. Okay, so this is the first case we want to discuss, and actually we have a second special case when, so I can take this away, right? Okay. So the second case is when we have a open termination. So in that case, we have a transmission line And this transmission line is terminated with an open circuit. Okay? So now this ZL is infinity, and this is VL, this is LL, and the extra condition we have here on the boundary is actually IL is equal to 0, right? Okay? Which means, again, if we have this z-axis here, this is z equals 0, z equals negative L. Okay, again, I of 0 is equal to V plus over Z naught minus V minus over Z naught. Okay, which is 1 over Z naught V plus times 1 minus gamma L, right, is equal to 0. Okay, so that means gamma L must be equal to 1. So whatever the incoming, the red traveling wave is, it is reflected totally and travels back. Okay, so gamma L is equal to 1. And in this case, the input impedance, let's say this Z of negative L, Z of negative L is equal to negative J Z naught cotangent of beta L, okay, which we write it as Jx. And if we plot this x, so the electrical length beta L x, it just looks like a cotangent function. Okay, so let me see. I think it looks like this, right? The other way? Like this? Let me double check. Let me double check. Yeah, it looks like this. Right? Okay, so this is cotangent. I did a very bad drawing. But anyway, you can see that this reactance is still behaving like a capacitor, and then behave like an inductor, and then it's a periodic behavior. Okay? So it's totally similar to the short termination case. Okay? So these are the general for the general terminated case and two special cases. And one thing actually we learned from these cases is that we can see that gamma L in this case is equal to ZL minus Z naught over ZL plus Z naught, which is, if we use the normalized impedance, ZNL minus 1 ZNL plus 1, right? And on the same time, ZNL is equal to 1 plus gamma L over 1 minus gamma L. Okay, so this is at Z equals 0. And actually this is true, I mean these relations are true for arbitrary Z-axis. Okay, which means gamma of Z is equal to Z normalized impedance, Zn of Z minus 1 over Zn of Z plus 1. Okay, and Zn of Z is equal to 1 plus gamma Z divided by 1 minus gamma of Z. Okay, so These two relations are true for arbitrary z-axis, and you can see that their relation, if we want to calculate gamma z from zn, or we want to calculate zn from gamma z, their expressions are kind of similar, right? Actually, these two expressions, they form a so-called bilinear mapping, okay? And actually, in complex function analysis, they form a conformal mapping, which means if I have a z-plane, so suppose this is real z or zn, real zn, this is the imaginary part of zn, and if I have a straight line here with a fixed real part of zn, well, this transformation will give us, if we have the, let me see, if we have this real gamma plane, and this is imaginary gamma plane, it will transform this straight line in the z-plane to actually to a circle, for example here. Okay, and if we move the straight line to another place, we'll have another circle. And similarly, a straight line in the gamma plane will be transformed to a circle in the z-plane. Okay, so actually, people take advantage of this conformal mapping, and they design a graphical calculator which is called the Smith chart. Okay, so let me show the Smith chart. Okay, so this is what the Smith chart looks like. Actually, what you can use this Smith chart is, you can see there are many circles. Okay, actually there are two groups of circles. One is whose center is on this horizontal line, like this circle, okay? And we have another group of circles whose center is out of scope, is out of this big circle, which is like this, okay? And like this. And for both the two groups of circles, actually you have a number associated with them. Let's say for this, we'll call this inner circle, okay? For this inner circle, you have a number 3 associated with this inner circle. And for this outer circle, this one, we also have a number 3, right? Which means, if I have a point, let's say the point is here. This point is the intersection between the inner circle 2 here and the outer circle 3, which means this point represents the normalized impedance 3 plus J2. Okay, so you can find, well, this is a 1-1 mapping between any normalized impedance and the Smith chart. Okay, and you can read in the lecture note that the Smith chart is very convenient when you want to do, for example, impedance matching, or if you have a transmission line connected to a load and you want to calculate the reflection coefficient. Yes?
I'm correct, I think that point is 3 plus J3.
Oh yeah, 2 plus J3, sorry. 2 plus J3, where this horizontal axis represents the real part of your impedance, and these numbers on the outer circle represents the imaginary part of your impedance. Okay, so one thing in particular is actually, I cannot write here, so one thing is, I'll switch back to the doc-cam. One thing we need to, which is very useful, is that actually when you have when you have a load with the transmission line, okay, so you know that this is z equals 0, z equals negative L. You know that the reflection coefficient gamma of negative L is equal to gamma L e to the negative j 2 beta L, which is gamma L e to the negative j 4 pi times L over lambda, okay, where we use the fact that beta is equal to 2 pi over lambda, okay. So you can see that when L equals half of the wavelength, beta L is equal to pi. So e to the negative j 2 beta L is equal to e to the negative j 2 pi, which is just 1, which means the reflection coefficient is back to gamma L again, okay. So gamma negative lambda over 2 is equal to gamma L, okay. Actually, you can find the reflection coefficient with arbitrary L connected to this load by using the Smith chart. We know that the reflection coefficient is less than 1, right? Because we have a passive load ZL, so it cannot generate energy. So gamma L is equal to or less than 1, okay? So actually, if you can find like gamma L is equal to 1, then gamma L is the corresponding gamma L is at this point, okay, which is equal to the radius of this big circle. And if gamma L has a phase, then you can just move that gamma L in this complex plane, where the region of the complex plane is here, okay. You can find gamma L in this complex plane, and when you have transmission line as a, let's say, suppose this gamma L is initially here, okay, and then you have a transmission line. As L increases, the gamma z will be just gamma z will move just clockwise this way along a circle whose center is at this center here, okay. And when L is equal to half pi, you have the antinode about the center. Gamma L is here. And when L is equal to lambda, you're back to the gamma L. So that's a convenient way for you to find the generalized reflection coefficient. Okay, I cannot draw here, so you can read in the lecture note, which can have you have a more clear understanding. Okay. So we have this Smith chart, and let me see. Another thing we need to learn about is the so-called voltage standing wave ratio. Okay, so again, we have a transmission line which is terminated or arbitrary transmission line. Okay, and we know that the voltage on this transmission line is V of Z, which is equal to V naught e to the negative j beta Z plus gamma L V naught e to the j beta Z, right? And this can be written as V naught e to the negative j beta z times 1 plus gamma L e to the 2j beta z, right? And you can see that the amplitude of Vz is not a constant along the transmission line. If you change the value of z, the amplitude of V can change as well. Okay? So the amplitude of Vz is actually equal to the amplitude of V naught, and this term, its amplitude is just 0, okay, times the amplitude of 1 plus gamma L e to the 2j beta z. Okay? So for a given system, V naught is a constant from the source, okay, but this term is changing. Okay? So if you draw a coordinate system like this, this is the real axis and this is the imaginary axis. Okay, suppose this is 1. Okay, the largest value of this term, the largest amplitude as you change the value of z, is actually 1 plus the amplitude of gamma L, right? And the smallest value of this term is actually 1 minus the amplitude of gamma L, right? So as you increase the value, the value of z, actually you probably start here, then go to here, then go to here. So this circle is actually 1 plus gamma L e to the 2j beta z. Okay? So as you can see, the amplitude of the voltage on the transmission line has maximum value, which is V max is equal to 1 plus the magnitude of gamma L, right? And the voltage also have a minimum value, V min, is equal to 1 minus the amplitude of gamma L. Okay? And if you draw the magnitude of the voltage, let's say this is Z, this is V of Z, it probably looks like this. In periodic manner, okay, where we have V max here and V min here. Okay, and actually the ratio between V max and V min is called the voltage standing wave ratio, which is VSWR is equal to V max over V min, which is 1 plus gamma L magnitude over 1 minus the magnitude of gamma L. Okay? The reason we define this quantity is that it's not very easy for engineers to measure the voltage in a microwave system, because as the frequency increases, the voltage between 2 points is not uniquely defined. Okay, because you have varying magnetic field. If you measure this electric field, the integral of the electric field along different paths, although the starting point and ending point are the same, but the path is different, you have different voltage. So the voltage is not unique anymore. Okay, but we can actually measure the VSWR, and from the VSWR we can deduce the, for example, reflection coefficient, input impedance, things like that. It's just very easy for us to measure a microwave circuit or microwave system. And more detailed knowledge can be found in the lecture note, and you can read the lecture note after class. Okay? So basically, this is for lecture 16. And does anyone have Any questions before we move on? Okay, if not, let's move on to lecture 17, where in lecture 17 we'll study multi-junction transmission lines. Okay, and also in lecture 17 we also have duality principle, but I'm not sure we have enough time or not. If we do, we'll cover the duality principle as well. Okay, so actually transmission lines are very widely used in modern technologies. Okay, and here we have some pictures of different transmission lines, like the coaxial cable, optical fibers, waveguides. Waveguides are also a kind of transmission lines, and microstrip line, and also electrical power line and twisted pair line, pair wire. And this is another example where we have the microwave integrated circuit. Okay, and all these circuits are printed on a PCB board. Okay, and you can see that these structures here, also here, they are just transmission lines. We use transmission lines to connect different components or elements in the circuit. Okay, but also you can see that different transmission lines here, like this one and this one, they have different structure, like different width, different material probably. So which means their parameters are different, like the characteristic impedance or the wave number beta of different transmission lines are different. So we have a question, is that what happens if we connect different transmission lines together? How can we analyze such a structure, such a circuit? Okay, so that's why we study multi-junction transmission lines in this class, in this lecture. Okay, so let's say, for example, we have a transmission line, multi-junction transmission line like this. Okay, so we have the first section of transmission line, we have the second section of transmission line, and this part is infinitely long. Okay. Okay, so the first part, suppose we have the characteristic impedance Z01, okay, and this part we have Z02, and the length of the first part is L1, and the length of the second part L2 is infinity. Okay, and so what can we do about this? Well, actually, we can first find out the input impedance. If we look from here, let's say this is Z in 2. Okay, and of course, since the second section on this transmission line has is infinitely long, so that we know that because we know that for the second part of the transmission line, if we look from here, we have gamma of Z. Let me write it as gamma 2 of Z, because we are looking from the second transmission line, and Z in, right? And we know that gamma 2 of Z is equal to 0, right? Because this transmission line is infinitely long, we will never have a reflected wave. Okay, so gamma Z is always 0. Okay, so Z in 2 is equal to Z02 times 1 plus gamma of Z, gamma 2 of Z, over 1 minus gamma 2 of Z. Okay, and we know gamma 2 of z is 0, so it's just the characteristic impedance of the second transmission line. Okay, so the input impedance, if we look from this point, is just CO2. Okay, which means the VI relation on this port here is equivalent to a load ZL equals ZO2, right? So we can draw an equivalent circuit like this. ZL equals ZO2. Okay, so these two circuits are equivalent to each other. Okay, everybody agrees? Okay, so this is nothing but a terminated transmission line. We just learned about the general expressions for the input impedance, for the reflection coefficient, everything, right? So we can write the, let's say this is the first transmission line, and again, for this equivalent circuit, we have z axis here. Here is z equals 0. Here is z equals negative L. The input impedance, if we look from here, z1 of z and gamma 1 z. We can write down the expressions. z1 of z is equal to z01 times 1 plus gamma 1 z over 1 minus gamma 1 z, right? Which is z01 times 1 plus gamma L times e to the 2j beta z over 1 minus gamma L e to the 2j beta z, where gamma L is equal to ZL minus Z01 over ZL plus Z01, which is because ZL is nothing but ZO2, right? So it's equal to ZO2 minus Z01 over ZO2 plus Z01, right? Okay? And we can find Z in 1 at where Z equals negative L1, it's equal to Z01 1 plus gamma 1 negative L1 1 minus gamma 1 negative L1. Okay, so we can find the input impedance of the first, if we look from the first transmission line, Z01. Okay, we can find the input impedance, the reflection coefficient, the reflection coefficient gamma 1z, which is gamma L times e to the 2j beta z. We just learned everything from lecture 16. Okay, so you can see that the idea here is we have multi-junction transmission lines, but we can always find the equivalent circuit to the rightmost part of this circuit, right? And then we have the equivalent impedance ZL equals ZO2, and then we simplify this circuit to a terminated transmission line, which we have learned how to analyze this problem. Okay, actually we can use this idea, this strategy recursively, that if we have a transmission line, multi-junction transmission line like this, okay, we have 3 different transmission lines. Okay, and this is L1, L2, L3 is equal to infinity, and this is Z01, Z02, Z03. Okay, so the first step we can do is, again, this is an infinitely long transmission line. Its input impedance is just 0.3, right? Okay, so this is equivalent to where ZL is equal to Z03, right? Okay, they are equivalent. So now we have this new equivalent circuit, and we can define the reflection coefficient here to be gamma 1 2 tilde, and the input impedance to be Z in, let's say this is Z in 2, because we are looking into the second transmission line. Okay, so how do we find Z in 2 and gamma 1 2 tilde? Any ideas? Yeah.
Did you use the general expression to calculate them from the
Right, because if we just look to the right, the equivalent circuit has nothing to do with its left, right? So the right-hand side part is just a transmission line with a termination. Okay, so again we can find the input impedance and the reflection coefficient for the right-hand side part. Okay, so Z in 2 is equal to, now let's write Z in 2 is equal to, well, let's write the Z2 of Z first. Okay, that means I look from here at arbitrary Z. Okay, again this is Z equals 0, positive Z, Z equals negative L here. Okay, if we look at arbitrary point Z equals negative L, but still we are looking in somewhere in the second transmission line. We have Z2 of Z is equal to Z02, 1 plus gamma 2 of Z over 1 minus gamma 2 of Z. Okay, which is Z02, 1 plus gamma L e to the negative 2 j beta 2 Z. Okay, here we have beta 2, here we have beta 1. Okay, divided by 1 minus gamma L e to the negative 2 j beta 2 Z. Right, so this is the input impedance if we look from the second transmission line. Okay, and here, of course, gamma L is equal to ZL minus ZO2 over ZL plus ZO2, which is ZO3 minus ZO2 over ZO3 plus ZO2, right? Okay, and we can find the generalized coefficient, reflection coefficient, gamma 1 2 here, gamma 1 2 tilde, to be Z into minus Z01, because in this case, this circuit here, this one, can be simplified or equivalent to this L1. This is Z in 2, right? ZL equals Z in 2, 2, right? Okay. And we have beta 1 Z01 here. Okay, so again, we just have a transmission line with a impedance termination. Okay, so the reflection coefficient here is actually gamma 1, 2 tilde, right? And this reflection coefficient in this circuit is nothing but gamma L, okay, which is Z in 2 minus Z01 divided by Z in 2 plus Z01. Okay? Okay, so we have this gamma 1, 2 tilde, and this gamma 1, 2 tilde actually take into account the reflection from Z03 and the reflection between transmission line and 2. So it's a general reflection coefficient. It considers all the reflected waves. Okay? So we can write this as Z02 1 plus gamma 2 of Z 1 minus gamma 2 of Z minus Z01 over Z02 times 1 plus gamma 2 of Z over 1 minus gamma 2 of Z plus Z01. Okay, so we did nothing but we just plug Z2 of Z equals to this one up to here. Okay, so here Z is equal to negative L2. Okay, because the length of the second transmission line is L2. Okay, so what we have here is actually, well, if you do some algebra and rearrange those terms, we have gamma 1, 2 plus gamma divided by 1 plus gamma 1, 2 times gamma. So here, gamma 1, 2, I'll give the expression later, and gamma is equal to gamma L e to the negative 2j beta 2 L2. Gamma 1, this is 1 plus gamma 1, 2, this is gamma L3 e to the negative 2j beta 2 L2. Here gamma L3 means this equivalent load. Okay, so in this expression, gamma 1, 2 is equal to Z02 minus Z01 over Z02 plus Z01. And this is called the local reflection coefficient. Okay, that means if we don't have this load and we suppose this second transmission line is infinitely long, then the reflection coefficient gamma 1, 2 is just this one. Okay, that's called local reflection coefficient. And gamma L3 is nothing but Z03 minus Z02 over Z03 plus Z02. Okay? So we are just trying to figure out the equivalent circuit in a recursive manner, and then we can solve this problem. Okay? And actually, this expression here is a very powerful formula that it's very convenient for you to find the input impedance and reflection coefficient for multi-junction transmission lines. Okay, for example, if you have a transmission line with 3 sections and a load here, Okay, this is Z01, L1, beta 1, L2, beta 2, L3, beta 3, Z03. Okay, so in this case, if you have the reflection coefficient gamma 23 tilde and Z in 3 here, and gamma 12 tilde and Z in 2 here. Okay, so we can just use this formula. Okay, first find gamma 23 is equal to gamma 23, the local reflection coefficient. Okay, it's nothing but Z03 minus Z02 over Z03 plus Z02 time plus gamma L, which is determined by ZL here, and e to the 2j beta 3 L3 1 plus gamma 23 gamma L e to the negative 2j beta 3 L3. Okay, so we have this general reflection coefficient gamma 23 tilde. Okay, and if we want to further find gamma 12 tilde, we can use this formula again. Okay, that will be gamma 12, the local reflection coefficient, plus gamma 23 tilde. Okay, e to the negative 2j beta 2 L2. Okay, because if you draw the equivalent circuit here, okay, this is nothing but Z in 2, and the reflection coefficient due to this Z in 2 is nothing but this gamma 23 tilde. Okay, so again we have gamma 12 gamma 23 tilde e to the negative 2j beta 2 L2. Okay, and also you can find the input impedance Z in 2, which is Z01 1 plus gamma 12 tilde 1 minus gamma 12 tilde. Okay, so you can seek for the solution, the reflection coefficient and the input impedance section by section, then until you reach the leftmost section. Okay, are there any questions before we end the class? Okay, if not, I'll end here, and hopefully you'll learn something from me. Okay.